Okay, so let's finish our chapter today, okay, in 1 hour. And that will be it for the midterm. So today we're going to worry about existence of random variables. So before talking about the existence of random variables, let me remind you a few things. So let's say we have some random variable from omega to r bar, okay? So remember we talked about the distribution of x, and one function that is attached to the distribution of a random variable was the cumulative distribution function. So the cumulative distribution function is defined as the probability that x takes values less than x, little x. So this as a function of little x is called the cumulative distribution function. So there are some nice properties of cumulative distribution functions. I remember I mentioned some of those once. So let me remind them again. So if you increase this little x here, you have a larger set. Therefore, the probability also increases. So it is an increasing function. So f is increasing, meaning that if you have x1 less than x2, then fx1 is less than fx2. F is right continuous. And this is a result of the fact that we define it using less equal relation, but not strictly less than relation. You would get the left continuous version if you have the strict inequality. So this means what? So if you approach a point from the right, meaning that if you look at the right limit of f as f of y as y approaches to x from the right, so y is going down to x from the right, therefore this limit is supposed to be equal to f of x. And also if you look at the limit of f, so f plus infinity, I define it as the limit of f as x goes to plus infinity. This is the probability that x is less than plus infinity. And f of minus infinity is going to give you the probability that x is equal to minus infinity. So if x is real valued almost surely, then this is 1 and this is 0. And also this function f has left limits. So f is left limited. So in other words, this right limit, left limit exists. So a picture like this we observe. So let's say we have x here and f of x here. So these are values between 0 and 1. Okay, so it may stay constant for a while. It may have a jump. And it may touch 1, or it may stay below 1 forever. So let me draw like that. Okay? And this is the left limit of the function at this point. So if you call it x, okay? X, the function f makes a jump at the point x. So this jump size is exactly the probability that x is equal to x. So in fact, so this left limit exists and is equal to the probability that x is strictly less than little x. Okay, so this value is the probability that x is less equal x, and this is the value. This is the probability that x is strictly less than x. Therefore, the gap, the size of the jump, gives you the exact probability that it takes this certain value, little x. So we can say f is continuous at x if and only if the probability that x takes this fixed value is 0, right? So the jump size is really the mismatch between the less equal and strictly less type of probabilities, and it gives us the atoms. So if there is a jump at any point, this means it is an atom of the distribution of x. And you see here that the cumulative distribution function doesn't have to strictly increase. It can stay constant for a while. So let's say we have some x bar here up to x bar plus epsilon. Okay. So the values of the cumulative distribution function at those 2 points are equal. So this means the probability that x is between x bar and x bar plus epsilon is 0, because this is fx bar plus epsilon minus fx bar. So this is just 0 since the two values are equal. And these two types of properties or behaviors, let's say, so staying constant for a while and also having jumps, might make it an interesting kind of function. In other words, maybe you're not able to define its inverse. So if it were strictly increasing and if it has no jumps, then you can define its inverse function, right? It's always strictly increasing, and you just need to find the set of values. It's a set of all possible values, namely here in this axis. You can just define the inverse function. Okay. But this can be observed if you have a mixed type of random variable, like the example that we discussed last week. So its cumulative distribution function has some jumps because there are atoms of the distribution. And also, there is a continuous part of the distribution. I mean, the part where the cumulative distribution function is continuous and has some increases like this. So you can observe both types of behaviors. You can have a part that stays constant. You can have a part that has a jump. So it is possible to observe all sorts of shapes. But it is always increasing and right continuous. Okay? So let's define a cumulative distribution function without reference to a random variable. Okay? So a function f, so I'm not saying it is the cumulative distribution function of a random variable. I'm just defining it as an abstract function, okay? So f on R to 0, 1 is called a cumulative distribution function if it is increasing and right continuous. Let me add here cumulative distribution function of x, okay? Of x. So if you have some probability space on which you have a numerical random variable, then we know that its cumulative distribution function, f, is well defined by this definition, right? And it is a cumulative distribution function according to this new definition. It is right continuous and increasing. So now the question about the existence of random variables is as follows. Given a cumulative distribution function, does there exist a probability space and a random variable such that the cumulative distribution function of that random variable is the given cumulative distribution function? So this is our question. So given CDF F, does there exist a probability space on which there is a numerical random variable whose CDF is F? Okay. Any questions so far? Is the question clear? Is this question clear? So the answer will be yes to this question. And this will mean what? So just give me one right continuous and increasing function on the real line mapping into 0 to 1 interval, unit interval. Then I can give you a random variable on some probability space whose distribution function, cumulative distribution function, is f. Okay? So in other words, to define a distribution of a random variable, all you need is a cumulative distribution function. Namely, all you need is a function that is increasing and right continuous. So whenever you have such a function, there is a corresponding probability space and a random variable admitting that distribution or admitting that cumulative distribution function. Okay? Because we always say, okay, let x be a Gaussian random variable, let y be a Cauchy random variable, et cetera, et cetera. So we always give examples of distributions, but do we really have those, do we really have probability spaces having such random variables? Okay? We always say let us assume there is such a random variable with that kind of a distribution, but the question of existence is never answered. So now we finish this chapter by answering this question. Okay? So let's start with an easy case, okay, to get some intuition. So as I said, the two kinds of interesting behaviors of a cumulative distribution function is that it may stay constant and it may have a jump, and some jumps. By the way, you can only have countably many jumps. But anyway, let's look at the nice case where there are no jumps and there is no place where it stays constant. So it is strictly increasing and continuous. So, okay, a simple case. Okay, suppose f is strictly increasing and continues. You may even assume that the limit as x goes to minus infinity is 0, and limit at plus infinity is 1, so that your picture looks like this. Okay, this is the picture for f. It's strictly increasing, never stays constant. So in that case, you can very nicely define the inverse function on 0 to 1 open interval, right? Since its limit is at minus infinity is 0, and at plus infinity its limit is 1, so we cover all possible values from 0 to 1, okay? So just give me 1 point, okay? I can give you f inverse u, right? And it is the unique point where the value of f is equal to u, because the function is strictly increasing. There is no other point that can give that value u, right? So in that case, in this case, f inverse from 0, 1 to r is well defined. As a function, right? It's the inverse function. So f inverse is a function, the inverse function, defined on 0, 1 interval, okay? Open interval. So we may see f inverse as a random variable on the probability space. Which probability space? 0, 1 with its Borel sigma algebra, and which measure? So if you have the interval 0, 1, which probability measure would you assign to that interval? What is the simplest measure on that interval, 0, 1? Which measure have we discussed on the real line? The Lebesgue measure. So on the interval 0, 1, it's a probability measure, right? Because the length of this interval is just 1. Now, this as a random variable has the following CDF. So let's calculate the CDF of f inverse as a random variable. What is the definition of the CDF of a random variable? Well, just look at the probability that that random variable takes a value that is less than some fixed value. Okay. So what is our probability measure? It is the Lebesgue measure. What is our random variable? F inverse. F inverse is less than some fixed point. Right? This is how we should define the CDF. Probability that random variable takes values less than little x. So what is this? It is the Lebesgue measure of the points u, 0, 1, such that f inverse u is less equal x. But this is equivalent to saying that u is less than f of x, because f is strictly increasing and continuous, so these are if and only if, right? So f inverse u is less than x if and only if u is less than f of x. So now what is this? What is this? Well, this is the Lebesgue measure of the values that are between 0 and f of x. So it is the Lebesgue measure of the interval 0 to f of x. Right? So what is the Lebesgue measure of this interval? I should include this part, right? U is between 0 and this f of x. So what is the Lebesgue measure of this interval? Just f of x, right? F of x is a number between 0 and 1, and we're measuring the length of it. So the length of this interval is just f of x. So indeed, we found a probability space on which there is a random variable whose cumulative distribution function is exactly f. So f inverse as a random variable on 0, 1 interval has f as its cumulative distribution function. This is the motivation, or this is the easy case, right, where you have an inverse function. So at least in the case where the cumulative distribution function, the given cumulative distribution function is strictly increasing and continuous, we answered the question, right? We already answered this question in that case, the simple case. So now what should we do in the general case? The general case. So in the general case, the issue is that the inverse is not well defined as a function because, for instance, on that picture, x bar and x bar plus epsilon, they have the same f value. So if we're at this point, what is the f inverse of this point? This, or this, or this, or this? We don't know. What we can do is to make a choice and define a sort of pseudo-inverse, okay? And we're going to give the following definition. So let's define a pseudo-inverse. For f, okay? And it's going to be the right continuous inverse Q and also the quantile Q is defined on the interval 0, 1 to r bar. Now it can have plus infinity as its value. So is defined by Q of u is the minimum of x values for which f of x is above u. Maybe we should draw some nice picture to see what can happen. Maybe 2 pictures, okay? We're going to draw 2 pictures. I'm first drawing the second picture for the CDF. Okay, so this is for f. This is for f. And now we're going to draw a second picture. So we have the x values here and the u values here. And we're going to draw a second picture, which is going to have the which is going to have this axis for u and this axis for x values. But the function is going to define for u values. So we have to look at it like this. So let's draw the q function. Let's draw the picture for the q function. Let me make this picture slightly easier. Okay, we're interested in really the parts where it's constant and it has a jump. Okay. So at the beginning, it's like a function that is invertible, right? That has an inverse. So for those values, it's not very difficult to draw the inverse function until this point. Okay. Now let's see what the inverse at that point is. Okay. Let's see how q is defined. So the infimum of x values for which f of x is strictly above u. What is the set of x values for which f of x is strictly above u? So let's say this is x1 and this is x2. Can you tell me the set of x values for which f is strictly above u? What is the set of x values for which f of f is strictly above u? Greater than x2, right? Not x1. Because here in this region, it is equal to u. Okay, so it doesn't satisfy this definition. So we only take values here. And the infimum of those values is just x2. Okay? So this means we define q of u as x2. Okay? So x1 is here. x2 is here, let's say. So we define it like this, with a jump. So you see, on the region where f stays constant, q makes a jump. So it shows the opposite behavior. There are two types of behaviors of f, right? Staying constant. So whenever f is staying constant, q is going to have a jump in a right continuous manner, just like f. Okay? And whenever f has a jump, it's going to stay constant. It's going to stay constant. So let's look at that part. Okay, so now we are here. So again, we continue like in an inverse function manner on this region. So let's look at u bar here, okay? Let's see what happens at u bar. Again, we need to look at the values of x for which f is strictly above u. So f is strictly above u. Well, at that point, we are strictly above u, and we are always above u, strictly above u, in the rest of our life. So the infimum of such values is just x bar. Okay? So let's say this is x bar here. So it's going to stay constant up to this point. It's going to stay constant, and then it's going to increase again. So this is the picture for Q. Let me write it this way, okay? So it is more or less an inverse function, but it is also well defined in the cases where f is not invertible. So we call it the right continuous inverse. And of course, if you change it to non-strict inequality, you would get a left continuous version, I guess, if I'm not wrong. Anyway, so there is also a left continuous type of quantile, but we want a right continuous one. Okay. By the way, here we need to assume that infimum of the empty set is just plus infinity. Okay. So sometimes there are no points where f is strictly above u. For instance, in the case where your function f stops at a point strictly below 1, in that case, if you look at a value that is very close to 1, its inverse is just defined as plus infinity, because this set is just empty, so the infimum of that empty set is just going to be plus infinity. So you might have a plus infinity region here. Okay. And similarly, there might be a minus infinity if you have a limit that is a limit at minus infinity that is strictly above u. Okay. So maybe some observations about Q. Again, I'm going to state them in the form of an exercise. So observe that Q is increasing and right continuous. And F and Q are pseudo-inverses of each other. In the sense that if you define further the pseudo-inverse of Q with the same definition, so if you define infimum of U values now, for which Q of U is strictly above X, that's going to give you f of X. So now I defined what? I defined the pseudo-inverse of Q. And some more observations. So if Q is real valued, then this means what? F at plus infinity is 1, and F at minus infinity is 0. And I think it's if and only if. So this kind of values, plus and minus infinity, can only appear on the endpoints of the interval 0, 1, close to the endpoints of interval 0, 1. And let's also state our observation about the relationship between f and q. So whenever f stays constant, q makes a jump there. And whenever f has a jump, q stays constant there. Okay? So q has a jump at u if and only if f stays constant at value u for a while. I'm stating things in informal terms. Q stays constant at value x for a while. This is if and only if with f has a jump at x. I think we're ready to give our important theorem, but let me wait. Any questions so far? So this is the quantile function, okay? This Q is the quantile function. And as we did in the simple case, where f was invertible, we're going to see q as well as a random variable on this probability space. So let f be a cumulative distribution function, namely it's just right continuous and increasing, and q its quantile function or pseudo-inverse. Okay. Then q as a random variable on this space has f as its cumulative distribution function. So there is a probability space with a random variable on it whose CDF is f. So the same thing works in the general case as well. Maybe we should just state the corollary first to show this point. Okay, let's first give a corollary. So let x be a random variable on some probability space with cumulative distribution function f. Okay, and let q be the corresponding quantile. So let u be a, let me say it this way. Let u be a uniform random variable, okay? Between 0 and 1 on some other probability space. Then q applied to u is has the same distribution, has f as its CDF, meaning that q of u and x have the same distribution, So this is left as an exercise, but we're going to prove the theorem. So what is the meaning of this result? Well, it is not just the quantile function which you force yourself to see as a random variable with distribution function, cumulative distribution function f. Indeed, you can just start with some uniformly distributed random variable over 0, 1 on an abstract probability space, and then just apply your quantile function. Let's say you calculated this quantile function in a concrete manner. You have the CDF, and you calculate this for every u. Now you have a formula for q. Just apply this formula for q to your uniformly distributed random variable. Okay? Then this is going to have f as its CDF. In other words, q of u is going to have the same distribution as x. And this is, in fact, a very important principle in simulation. Do you remember, if you've studied simulation somewhere else, do you remember something called an inverse transform technique? Yeah, so what is inverse transform technique? So you want to simulate random variables with certain distributions, okay? What you do, what the computer does is to create random variables or generate random numbers with respect to the uniform distribution. Okay? Then all you have to do is to apply the inverse function of f to those uniformly distributed numbers. Okay? So if you can generate uniformly distributed random variables, all you have to do is to apply the inverse function or the quantile function of your desired cumulative distribution function. then this is going to have the same distribution as x, as f, right? The CDF f. So let me write it as a remark, and then we will look at the proof of the theorem. Remark. So the corollary gives rise to the so-called inverse transform technique in simulation. So, meaning that to generate realizations of a random variable with CDF f, it suffices to generate realizations from the uniform distribution. Then we can just apply Q, which is this inverse transform there, to these realizations, and the new numbers form realizations from a random variable with CDF f. So if you just have a uniform distribution here on 0, 1, so all you have to do is to generate random numbers according to this distribution, okay, some realizations of u, and then just apply q to them. So q of u of omega 1, q of u of omega 2, q of u of omega 3, and you can see them as your realizations of x in some sense. In some sense, meaning that these quantities have the same distribution as f. They have the cumulative distribution function f in theory. Okay, and that's a way to generate random numbers according to some given distribution. Of course, it is not the only way, and sometimes the quantile function is very ugly, and maybe there is not even a closed form expression, so you look for other techniques. Okay, let's quickly look at the proof of this theorem. So all we have to do is to check that the probability that q is less than x is f of x. And this is the Lebesgue measure of the u's, where q of u is less equal x. Okay, so let's fix some x. And we're going to look at two cases. Okay, so what is q of u less than x, less equal x? So you fix some value, let's say x bar. So q of u is less equal x, means you look at the values of u from here all the way down to maybe 0, right? But if you fix a point at which f, let's see. Okay, if you look at a point at which the function is kind of invertible, so everything's nice, it is just one-to-one that q of u is less equal x if and only if u is less equal f of x. Okay, so let's look at the case where f does not stay constant after x. Okay, f does not stay constant after x. So we're not in this region. Okay, let's exclude this region. So if we're somewhere here, it is really if and only if. So we have Lebesgue u in 0, 1. Q of u is less than x. This is the same as saying u is less than f of x. Okay? And this is just Lebesgue measure of the interval 0 to f of x, which is going to give you f of x. So the case 2 is, let's say f stays constant for a while. After x, then you should check that you lose the equality option. So u is strictly less than f of x, but this does not matter in terms of the Lebesgue measure. So even if you look at the open version of this interval, you still have the length equal to f of x. So it doesn't really matter which case you look at. In Lebesgue measure, you're going to get the same value. So you always have the CDF of q is equal to f. So the only issue here is that do you have equality or you don't have equality? But for Lebesgue measure, this is just a singleton with 0 measure, so it doesn't change the end result. So if you're measuring if you're looking at the Lebesgue measure of this set, it's not going to change the end result. You always have this equal to f of x. So this means q, when you see it as a random variable on this interval with respect to the Lebesgue measure, which is your probability measure, then your CDF for q is f. Okay? So this is the proof of the theorem. But you can do it in a more careful way. You can worry about these inequalities, equalities, etc. And everything looks very nicely on the picture. If you just look at the picture, you will see what may go wrong, etc., etc. Okay? So just have that picture with q and f. Okay? And check if the proof is all right, and you can correct it if there are some typos, because there are just 2 types of behaviors as we observed, right? So other than that, everything is nice. Okay, so this brings us to the end of chapter 2, and we are done with random variables that are kind of univariate, okay? So we're going to have a 1 week break, and then after that break, on week 8, we're going to start with, namely, product spaces, random vectors, etc., etc. Okay? So thank you.